70 feet below the Arkansas farmland, Airman David Powell braces against a retractable work platform inside Launch Complex 374-7. In his hands, a 3-foot ratchet wrench. Below him, a pressurized fuel tank holding 11,000 gallons of Aerozine 50, a hypergolic propellant that ignites on contact with its oxidizer. An $8 hand tool above a $37 million weapon system. Powell reaches toward a pressure cap on the Stage 2 oxidizer tank. The socket engages. He applies torque. And then the ratchet head separates from the extension. The 8-pound socket begins its fall. 80 feet of empty air stand between the tumbling steel and the aluminum skin of America's most powerful nuclear missile. The socket strikes a thrust mount, ricochets, and accelerates toward the Stage 1 fuel tank. The tank wall is 3/100ths of an inch thick, thinner than a dime. The socket is falling at 80 feet per second. Earlier that evening, September 18, 1980, Van Buren County, Arkansas. Launch Complex 374-7 sits beneath a featureless concrete slab 3 miles north of Damascus, a town of 300 people. Underground, a Titan II intercontinental ballistic missile stands in a concrete silo 146 feet deep, its walls 8 feet thick. The missile itself rises 103 feet, 10 feet in diameter, weighing 330,000 pounds fully fueled. At its apex sits a W-53 thermonuclear warhead with a yield of 9 megatons. 600 times the destructive power of the bomb that leveled Hiroshima. The warhead alone weighs approximately 8,000 pounds. This is one of 54 Titan IIs scattered across Arkansas, Arizona, and Kansas, each one capable of reaching any target on the Soviet Union within 30 minutes. Tonight, 2 airmen from the Propellant Transfer System team have arrived for routine maintenance. At 6:18 p.m., Senior Airman David Powell and Airman Jeffrey Plum activate their suit environmental control units and descend the cableway toward the launch duct. Powell is 21 years old, a certified PTS technician. Plum is 19, still in training. Their assignment is straightforward. Check the pressure on the Stage 2 oxidizer tank and remove a vent cap. New regulations require a torque wrench for this procedure. Powell and Plum brought one from the base. However, they left it in their truck. Rather than climb back to the surface in their cumbersome IRFCO protective suits, Powell retrieves a ratchet and socket from the equipment area inside the silo. He does not check whether the socket is securely connected to the extension by its spring-loaded retaining pin. A decision born of convenience. The kind of shortcut workers take every day, in every industry, without consequence. Until consequence arrives, Powell and Plum reach the work platform at level 3 of the silo. The Titan II towers beside them, its smooth aluminum skin curving away into darkness above and below. The platform sways slightly as hydraulics engage. Powell braces against the curved silo wall and radios the launch control center. The team chief begins reading the procedure checklist over the radio. Step by step. Cap removal. Pressure check. Documentation. Powell positions the ratchet wrench on the Stage 2 oxidizer tank pressure cap. Below him, separated only by the interstage structure, sits the Stage 1 fuel tank. 11,300 gallons of Aerozine 50 fuel. Directly above that fuel sits 13,500 gallons of nitrogen tetroxide oxidizer. Hypergolic propellants, chemicals that ignite spontaneously the instant they touch each other. No spark required. No ignition system needed. Just contact. At approximately 6:30 p.m., Powell applies torque to the pressure cap. The socket slips free from the ratchet extension. In the confined space of the silo, the metallic clatter of the falling socket echoes off concrete and steel. 3 seconds of free fall. Reports differ on the exact drop distance, somewhere between 70 and 80 feet. The socket strikes a thrust mount near the base of the missile and ricochets. It is now traveling at approximately 80 feet per second. The socket impacts the Stage 1 fuel tank skin. The concentrated point load exceeds the aluminum's yield strength. The skin punctures. A hole opens, 3 to 4 inches across according to later estimates. Behind that thin wall, 11,000 gallons of pressurized fuel at 15 pounds per square inch begin forcing their way through the breach. Aerozine 50 sprays into the silo atmosphere. Powell watches the white vapor billow from the wound in the missile's side. Powell keys his radio. His message to the control center is immediate and factual. They have a fuel leak. Inside the launch control center, the missile combat crew watches warning indicators illuminate on their console panels. Deputy Commander Alan Childers processes what he is hearing. A punctured fuel tank. Hypergolic propellant venting into a confined space. Below that fuel tank sits the oxidizer tank. If the fuel reaches the oxidizer, or if the structural failure causes the missile to collapse, the resulting reaction will be instantaneous and catastrophic. Childers initiates the hazard checklist. Red-tabbed emergency procedures. The indicators continue to climb. Smoke appears in the launch duct camera feeds. Powell and Plum are ordered to evacuate immediately. They begin the climb back toward the surface, leaving behind a wounded missile and a silo filling with toxic, flammable vapor. The clock has started. To understand how an 8-pound socket could puncture a ballistic missile, you must understand the engineering choices made 2 decades earlier. In the late 1950s, Martin Marietta designed the Titan II for one purpose: to deliver a nuclear warhead across intercontinental distances. Every pound of structure was a pound subtracted from payload capacity or range. The engineers specified aluminum alloy panels, welded into fuel tanks whose walls formed the outer skin of the missile itself. The thickness of those walls? Approximately 3/100ths of an inch. To grasp how thin that is, consider a United States dime. The coin in your pocket is about 5/100ths of an inch thick. The fuel tank holding 11,000 gallons of explosive propellant was thinner than the coin you might use at a parking meter. That engineering choice added 300 miles to the missile's range. It also meant any object with sufficient mass and velocity could breach the tank. The Titan II's thin skin was not an oversight. It was a calculated trade. Martin Marietta engineers knew that every pound saved on structure translated directly to combat capability. A heavier missile needed more fuel to achieve the same trajectory, which required larger tanks, which added more weight, creating a vicious cycle of diminishing returns. So they optimized ruthlessly. The fuel tanks became the airframe. No separate fuselage, no redundant containment. Just welded aluminum panels, pressurized from within to maintain structural rigidity. At 15 pounds per square inch, the internal pressure kept the tank walls from buckling under their own weight and the stresses of launch. That pressure also meant any puncture would become a fountain. The design worked exactly as intended for 17 years of operational service. 54 missiles, standing ready in silos across 3 states. Then, a socket fell. There was no tether attaching Powell's socket to his tool belt. No lanyard, no safety line. Air Force procedures in 1980 did not require tool restraints for work inside Titan II silos. Standard socket sets were issued to propellant transfer system teams, the same ratchets and extensions you might find in any automotive garage. These crews worked on platforms 70 feet above pressurized tanks containing some of the most dangerous chemicals in the military inventory. Any dropped object became a kinetic projectile. The Air Force had procedures for nearly everything: checklists for fuel transfers, protocols for oxidizer handling, emergency responses for vapor leaks. However, they had no requirement that tools be physically secured to prevent them from falling. According to later accounts, sockets had been dropped before. Most times, they struck the platform or the silo floor without incident. Damascus was the time the odds ran out. The Titan II used propellants chosen specifically because they ignite on contact. Aerozine 50, the fuel, is a 50-50 mixture of hydrazine and unsymmetrical dimethylhydrazine. Nitrogen tetroxide serves as the oxidizer. When these two liquids meet, they react instantaneously. No igniter, no spark plug, no complex combustion sequence. This hypergolic property made the Titan II the fastest ICBM in the American arsenal. Unlike earlier missiles that required cryogenic liquid oxygen, which boiled off during storage, the Titan II could sit fully fueled for months. Launch time from receiving the order? Under 60 seconds. The same chemistry that made the missile so responsive also made it extraordinarily dangerous to maintain. The fuel Powell was watching spray into the silo was not merely flammable. It was toxic, corrosive, and capable of spontaneous ignition if it contacted even residual oxidizer. As Aerozine 50 sprayed from the punctured tank, it vaporized into the silo atmosphere. The fuel has a lower explosive limit of approximately 2 to 3% concentration in air. Below that threshold, the mixture is too lean to ignite. Above the upper explosive limit, around 95%, it becomes too rich. But anywhere in between, a single spark can trigger detonation. The silo contained approximately 200,000 cubic feet of airspace. As fuel continued to spray from the breech at an estimated rate of several gallons per minute, vapor concentration began climbing toward that critical 2% threshold. Strategic Air Command Headquarters in Omaha consulted Aerozine 50 vapor pressure tables. The math was unforgiving. With no way to stop the leak and no safe method to ventilate the silo, they were watching a chemical timer count toward detonation. Damascus was not the first warning. According to Air Force records disclosed after the accident, there had been 125 accidents at Titan II sites in Arkansas, Arizona, and Kansas between 1975 and 1979 alone. From March 1979 to September 1980, 10 additional leaks and accidents occurred at Arkansas Titan sites. Launch Complex 374-7 itself had experienced an oxidizer leak in January 1978 that released a toxic vapor cloud 3,000 feet long, 300 feet wide, drifting across U.S. Highway 65. Several civilians required hospitalization. In August 1978, 2 airmen died at a Titan II site near Rock, Kansas, when oxidizer sprayed during a fuel loading procedure. These incidents generated investigations, concern from local communities, even congressional inquiries. However, the core vulnerabilities remained: aging seals, hypergolic propellants, thin tank walls, and no requirement for tool restraints. The physics of the socket strike were straightforward and devastating. An 8-pound steel object falling 80 feet accumulates kinetic energy. After bouncing off the thrust mount, it struck the tank skin traveling at approximately 80 feet per second. That translates to roughly 55 miles per hour. The socket did not hit flat. It struck point first, concentrating all that energy into a contact area smaller than a silver dollar. The aluminum alloy wall, 0.03 of an inch thick, experienced a concentrated point load that exceeded its yield strength. The metal did not dent, it ruptured. Once breached, the 15 psi internal pressure did the rest. The fuel inside had been waiting, under compression, for 17 years. Now it had somewhere to go. The spray began immediately. Within seconds, vapor filled the lower levels of the silo. By 8:30 p.m., 2 hours after the puncture, the missile combat crew evacuated the underground launch control center. Powell and Plum had already reached the surface. The decision to evacuate was not made lightly. It meant abandoning the silo to whatever happened next. It meant leaving behind a 9-megaton nuclear warhead with no human beings present to monitor or respond. However, the alternative was worse. Aerozine 50 vapor is acutely toxic. Even in low concentrations, it causes chemical burns to eyes and lungs. In higher concentrations, it can be fatal within minutes. The crew could not remain in a space filling with poison gas. Security police began evacuating civilian residents from the surrounding area. Families within several miles of the complex were woken and told to leave their homes. Most had no idea a nuclear missile sat beneath the farmland they had lived beside for years. Inside the abandoned silo, fuel continued spraying from the punctured tank. The liquid pooled at level 8 near the base of the missile. As it accumulated, More of it vaporized into the air. The silo atmosphere became a saturating solution of Aerozine-50 vapor. Because hypergolic fuel is volatile at room temperature, the evaporation rate accelerated. Camera feeds from the Launch Control Center, now monitored from a remote location, showed increasingly dense white vapor obscuring the missile. No one knew the exact concentration. The Air Force had no real-time vapor sensors positioned inside the silo. They were operating blind, trying to estimate how fast the tank was emptying and how quickly the vapor was accumulating. What they knew for certain was that the concentration was climbing, and somewhere above 2%, the entire silo would become a fuel-air bomb. Strategic Air Command faced a secondary nightmare scenario. The Stage 1 fuel tank was not just leaking, it was emptying. As 11,000 gallons of Aerozine-50 drained away, the tank lost the internal pressure that gave it structural rigidity. Without that pressure, the thin aluminum walls could buckle. If the fuel tank collapsed, the weight of everything above it would come down. The oxidizer tank, the interstage structure, the entire second stage, and the W-53 Warhead. A collapsing missile would rupture the oxidizer tank. 13,000 gallons of nitrogen tetroxide would cascade into a silo already saturated with fuel vapor. The resulting hypergolic reaction would not be a fire, it would be an instantaneous, catastrophic explosion. The warhead would be engulfed, and no one knew whether the safety systems could survive that. Hours passed. In conference rooms at Strategic Air Command headquarters in Omaha, officers and engineers searched for solutions. They found none. According to later accounts, there was no approved procedure for re-entering a Titan II silo with an active hypergolic fuel leak. The procedures covered fuel transfers, oxidizer handling, routine maintenance. They did not cover this. No one had planned for a scenario where a socket wrench punctured a pressurized fuel tank and the crew was forced to evacuate, leaving a nuclear warhead unattended in a silo filling with explosive vapor. Improvisation became the only option. However, improvisation in a nuclear weapons environment carries its own risks. Every decision had to balance the danger of action against the danger of inaction. And every minute that passed brought the vapor concentration closer to the explosive threshold. Shortly after 1 a.m. on September 19, nearly 7 hours after the puncture, Senior Airmen Greg Devlin and Rex Huckel received orders to enter the complex. Their mission? Assess the damage and determine vapor concentration. However, they faced an immediate problem. The complex was locked. When the crew evacuated, they sealed the facility. With no one inside to operate the electronic locks, Devlin and Huckel could not use the normal entry procedures. They were ordered to cut through the security fence using 3-foot bolt cutters. They descended 15 steps to the underground entry portal and used a crowbar to force open the steel-framed door. 2 airmen, breaking into a nuclear missile complex. Because there was no other way in, Devlin and Huckel wore self-contained breathing apparatus, standard SCBA gear similar to what firefighters use. Their air supply was rated for approximately 30 minutes. They descended into the complex and reached the blast doors, massive steel barriers designed to protect the control center from nuclear attack. The doors required manual operation, pumping open a 6,000-pound mechanism. However, their air was running low. Time was running out before they could complete the task. The vapor concentration they encountered was already severe. According to Devlin's later account, the atmosphere was eating at their protective suits. They had to withdraw before completing their assessment. 2 men, racing against their own air supply, trying to get readings from a silo they could barely see through the vapor. The mission was incomplete. Another team would have to try. Devlin and Huckel were relieved by a second team, Sergeant Jeff Kennedy and Senior Airman David Livingston. Kennedy was a quality control technician with 6 years of Air Force experience. Livingston was 22 years old, a native of Heath, Ohio. The 2 men were friends. They had worked together before. Now they proceeded past the security gate and unlocked portal doors that Devlin and Huckel had forced open. They reached blast door number 6. Their vapor detectors immediately indicated an explosive atmosphere. The readings were maxed out. Kennedy later testified that the concentration indicators showed 8 red warning lights. The silo was saturated. They reported their findings and were ordered to evacuate. However, the crisis was not over. Someone would have to go back in. According to Kennedy's testimony before the Accident Investigation Board, he then did something that would later earn him both a medal and a reprimand. Ordered to stay away from the complex, he disobeyed. Kennedy took it upon himself to re-enter the silo through an emergency escape hatch. He believed the tank readings were essential for any rescue or stabilization effort. No one ordered him to go. He went anyway. Kennedy descended into the vapor-filled silo alone. What he found confirmed the worst fears. The fuel was streaming from the Stage 1 tank. The vapor was so dense it was visibly degrading his protective suit. He recorded the readings and fled back to the surface. When asked later why he disobeyed the direct order, Kennedy stated simply that he thought the readings were of the utmost importance. At approximately 2:45 a.m., nearly 8.5 hours after the puncture, Kennedy and Livingston received a new order. They were to re-enter the complex and turn on an exhaust fan, an attempt to ventilate the silo and reduce vapor concentration. It was a desperate measure. Activating electrical equipment in an atmosphere already at explosive concentration carried obvious risks. Any spark could trigger ignition. However, doing nothing meant watching the vapor continue to build until something else provided the ignition source. Kennedy and Livingston proceeded into the complex. Both men understood the danger. Both went anyway. They reached the exhaust fan control. Livingston, the younger of the two, entered the silo to carry out the order. Kennedy waited near the blast door. The time was approximately 3 a.m. The ignition source remains officially unknown. According to the investigation board, the most likely cause was electrical arcing from the exhaust fan motor. Other possibilities included static discharge from the protective suits or spontaneous ignition from oxidizer contact. What is certain is that at approximately 3 a.m. on September 19, 1980, the fuel-air mixture inside the silo reached its ignition point. The Aerozine 50 vapor, saturating the atmosphere at or above the lower explosive limit, detonated. The chemical energy stored in that vapor cloud released instantaneously. An overpressure wave began propagating through the silo at approximately 1,100 feet per second, faster than the speed of sound. Everything in its path would be destroyed or displaced, including a 740-ton concrete and steel door. The silo closure door weighed 740 tons. It was constructed of reinforced concrete and steel, designed to protect the missile from nearby nuclear detonations. It could be opened in 17 to 20 seconds for launch operations. In the first fraction of a second after ignition, the overpressure wave struck the underside of that door with the full force of a fuel-air explosion. The mounting bolts sheared. Reports differ on how far the door traveled. Some accounts say 200 feet into the air. Others say it landed 600 feet northeast of the complex. What witnesses agree on is that the door, weighing as much as several hundred automobiles, was blown completely clear of the silo and thrown like a discarded lid. The mouth of the silo gaped open to the Arkansas night sky. With the silo door gone, the overpressure wave had nowhere to go but up. The Titan II missile, 103 feet of aluminum and fuel and oxidizer, was torn apart by the explosion. The Stage 1 and Stage 2 structures failed catastrophically. However, at the top of the stack sat the re-entry vehicle containing the W-53 Warhead. The force of the explosion propelled the Warhead assembly out of the silo. According to the investigation report, the second stage exploded once it cleared the silo rim. The Warhead separated from the disintegrating missile and followed a ballistic arc through the night air. Reports vary on exactly how far it traveled, somewhere between 100 feet and several hundred yards from the launch complex. The most powerful nuclear weapon in the American arsenal was airborne, uncontrolled, and tumbling toward the Arkansas farmland. At the moment of explosion, Greg Devlin was standing at the entry gate, half-suited in his RFHCO protective gear, waiting for Kennedy and Livingston to emerge. The blast wave hit him like a physical wall. According to his later account, he was thrown 50 to 60 feet through the air. He landed on his back with concrete, steel, and flames flying past his face. Someone screamed for him to run. He did. A chunk of concrete the size of a school bus landed where he had been lying moments before. More debris struck him. A steel rebar rod shattered his ankle. He suffered severe burns to his face, neck, and back. Others scattered across the complex perimeter suffered similar injuries. 21 people in total were wounded. However, they were the fortunate ones. They were outside the silo when it exploded. David Livingston was closer to the explosion than anyone else who survived. He had been inside the silo when the vapor ignited. The blast wave caught him near the entry portal. He was thrown clear but sustained massive injuries from the overpressure and debris. Kennedy, waiting near the blast door, was also caught in the explosion and suffered severe respiratory damage from inhaling oxidizer. Both men were presumed dead by those at the perimeter. Both were eventually located and evacuated. Livingston reached the hospital alive. However, his injuries were fatal. He died later that day, the only person killed in the Damascus explosion. He was 22 years old. He was posthumously promoted to staff sergeant. A building at Little Rock Air Force Base now bears his name. The W-53 Warhead struck the ground in a field adjacent to the launch complex. According to investigation records, it landed approximately 100 feet from the entry gate. Some accounts place it farther, perhaps a quarter-mile away in a drainage ditch. What every account agrees on is what did not happen. The warhead did not detonate. The conventional explosives surrounding the nuclear core did not fire. The safety interlocks, designed to prevent accidental detonation, held. The core of the W-53 contained highly enriched uranium rather than plutonium, which meant even the casing breach that occurred did not result in significant radioactive contamination. The most powerful thermonuclear weapon ever deployed on an American missile lay in an Arkansas field. Damaged, but intact. Its 9-megaton yield still safely contained. A nuclear weapon cannot detonate accidentally through simple impact or fire. This is by design. The W-53, like all American nuclear weapons, contained multiple safety mechanisms specifically engineered to prevent unauthorized or unintended detonation. The weapon required a precise sequence of electrical and mechanical events to arm. Strong links and weak links, in weapons engineering terminology. Strong links that must be deliberately activated, weak links that fail under abnormal conditions, breaking the firing circuit. The explosion at Damascus provided exactly the kind of abnormal conditions the safety systems were designed to survive. Fire, overpressure, impact, tumbling flight. Every one of those stresses was anticipated by the weapons designers. The warhead performed exactly as intended in an accident scenario. It did not explode. At daybreak on September 19th, the scale of destruction became visible. The silo gaped open, a smoking crater where a 146-foot deep concrete shaft had once contained an intercontinental ballistic missile. The 740-ton door lay several hundred feet away. Twisted metal and concrete debris spread across hundreds of acres. The Air Force dispatched recovery teams. Their first priority was the warhead. They located it in the field, damaged but structurally intact. Radiation monitors confirmed no plutonium dispersal. The uranium-based core had remained contained. The warhead was loaded onto a transport vehicle and returned to the Pantex weapons assembly plant in Texas. The launch complex would never be repaired. The most highly publicized disaster in the Titan II program was over. The reckoning was about to begin. President Jimmy Carter addressed the nation, reassuring the public that no radioactive material had leaked, and the situation was under control. Arkansas Governor Bill Clinton, briefed by Air Force officials, stated that no nuclear explosion could have occurred inside the silo. The Pentagon held press conferences. Officials emphasized the safety systems that had prevented catastrophe. However, the questions persisted. How had a dropped socket caused a $37 million missile to explode? Why had there been no procedure for re-entering a silo with a fuel leak? why were there no tool tethers required for work above pressurized fuel tanks? The Air Force convened a mishap investigation board. The investigation would examine equipment, procedures, training, and decisions. It would assign cause and recommend changes. It would not bring David Livingston back. The investigation board identified the root cause in straightforward terms: a dropped tool combined with thin-skinned fuel tanks and the absence of tool tethering protocols. The board documented the chain of events: Powell using a ratchet instead of the mandated torque wrench, the socket not properly secured to the extension, the fall, the bounce, the puncture, the evacuation, the re-entry attempts, the ignition. Each link in the chain traced back to engineering choices made decades earlier and procedural gaps that had never been closed. The board's report classified the incident as a broken arrow, the military designation for an accident involving nuclear weapons that does not result in nuclear detonation or risk of war. Damascus joined a list of broken arrow incidents stretching back to 1950. Jeff Kennedy, the man who twice descended into a vapor-filled silo to take readings, who disobeyed orders because he believed the information was essential, who was caught in the explosion and nearly killed, received 2 official responses from the Air Force. In May 1981, he was awarded the Airman's Medal for Heroism, along with Livingston, Devlin, Huckel, and others. However, Kennedy also received an official letter of reprimand for disobeying Colonel James Morris's direct order not to enter the complex. As one officer would later describe Strategic Air Command culture, to err is human, to forgive is not SAC policy. The men who risked their lives to understand what was happening inside the silo were recognized for their courage and punished for their insubordination. Both verdicts stood. David Powell, the airman who dropped the socket, was not publicly punished. The investigation determined that while human error initiated the incident, the systemic vulnerabilities made catastrophe nearly inevitable. Powell had used the wrong tool, yes. However, he had not been required to tether that tool. He had not designed the tank walls to be thinner than a dime. He had not created procedures that left crews without guidance when the unplanned occurred. According to later reports, Powell did not speak publicly about the accident for decades. He did not tell his wife or mother what had happened that night until 2014, 34 years later. The weight of that socket followed him in silence for most of his adult life. In the aftermath of Damascus, the Air Force mandated tool tethering for all propellant transfer system operations. Workers performing maintenance inside Titan II silos would now be required to physically secure their tools to their bodies. A lanyard, a simple strap connecting tool to technician, became standard procedure. The requirement that should have existed from the beginning was finally implemented. It was not a complex engineering solution. It was not expensive. It was the kind of basic safety measure that industries handling far less dangerous materials had long since adopted. However, it took a dropped socket, a punctured tank, an explosion, a thrown warhead, and a dead airman to make it happen. Some lessons require catastrophe before they are learned. On September 24, 1981, 1 year after Damascus, the Reagan administration announced plans to retire the entire Titan II program. The official rationale cited safety concerns, cost efficiency, and evolving nuclear strategy. More accurate solid-fuel Minuteman missiles would assume the deterrent role. The deactivation process began in 1982. Missiles were removed from silos and shipped for refurbishment or storage. Explosive demolition destroyed the launch ducts. The sites were left open for 6 months to allow Soviet satellite confirmation of their destruction, then filled with debris and covered with earth. By 1987, all 54 Titan IIs were gone. The most powerful single warhead ever deployed on an American missile had been retired. Damascus was one of the reasons why. Launch Complex 374-7 was never rebuilt. The Air Force demolished what remained of the structures, collected debris from 400 acres of surrounding farmland, pumped 100,000 gallons of contaminated water from the silo, and buried the site under gravel, soil, and concrete fill. The land returned to private ownership. Today, the crater where the silo once stood lies beneath an unassuming mound of earth in Van Buren County farmland. The site was listed on the National Register of Historic Places in February 2000. A marker notes what happened there. However, unless you knew what to look for, you would drive past without realizing that beneath that soil lies the grave of a $37 million weapon system, destroyed by an 8-pound tool. In 2013, investigative journalist Eric Schlosser published Command and Control: Nuclear Weapons, the Damascus Accident, and the Illusion of Safety. The book reconstructed the Damascus incident in meticulous detail, drawing on declassified documents, investigation reports, and interviews with survivors. Schlosser documented not only what happened that night, but the broader pattern of nuclear weapons accidents that had remained largely hidden from public view. According to his research, the Strategic Air Command had publicly acknowledged 32 broken arrow incidents. The actual number of accidents involving nuclear weapons was far higher. Damascus was not an anomaly. It was a data point in a pattern that the Cold War national security apparatus had worked to obscure. The Damascus accident codified an engineering lesson that extends far beyond nuclear weapons. Single-point failures in complex systems can originate from the simplest components. A $37 million intercontinental ballistic missile, designed to survive a Soviet first strike and deliver thermonuclear annihilation, was defeated by an $8 hand tool. Not because the missile was poorly designed for its intended purpose, but because the maintenance procedures failed to account for basic human physics. People drop things. When they work 70 feet above pressurized tanks containing instant ignition propellants, what they drop matters. The fix was not a redesigned fuel tank or a new guidance system. The fix was a piece of cord. After Damascus, Strategic Air Command officially blamed the incident on human error. Powell and Plum, who dropped the socket. Kennedy and the teams who went back in. The blame rolled downhill, as it often does in military organizations. However, the survivors knew the truth was more complex. As one officer would later observe, the X factor in any nuclear weapon system is human fallibility. The most powerful weapons ever created carry a threat built into them. That threat is the people who maintain them. No checklist eliminates fatigue. No procedure accounts for every possible combination of circumstances. No safety system anticipates every shortcut a tired worker might take at 6:30 on a Thursday evening. The Titan II is gone. However, the United States still maintains an arsenal of nuclear weapons. As of recent counts, approximately 5,000 warheads remain in the stockpile. Intercontinental ballistic missiles still stand in silos across the Great Plains. Their solid-fuel motors safer than the hypergolic propellants of the Titan II, but still requiring maintenance, still dependent on human operators, still subject to the same fundamental vulnerabilities that exist whenever people interact with machines designed for mass destruction. The lessons of Damascus have been incorporated into procedures and training. Whether they have been fully learned is a question that will only be answered the next time something goes wrong. Consider the alternative. The W-53 Warhead had a yield of 9 megatons. According to Office of Technology Assessment estimates, a 9-megaton airburst over a major city would produce approximately 2.4 million fatalities and 1.1 million injuries. The fireball alone would span miles. Radioactive fallout would drift for hundreds of miles depending on wind patterns. If the safety systems on the Damascus warhead had failed, if the conventional explosives had somehow detonated and triggered the nuclear core, the explosion would have devastated central Arkansas and deposited lethal radiation across the eastern United States. The socket did not merely puncture a fuel tank. It initiated a sequence that, with different luck, could have killed millions. The socket that fell that night weighed approximately 8 pounds. It was a standard piece of equipment, indistinguishable from thousands of others in Air Force inventories. After the explosion, it was never recovered. It lies somewhere beneath the fill dirt covering Launch Complex 374-7, or it was vaporized in the blast. Or it was collected as debris and disposed of without anyone recognizing its significance. A simple tool, a 3-second fall, a chain of consequences that led to an explosion, a thrown warhead, a dead airman, and a nation forced to confront the hidden dangers of its nuclear arsenal. The socket itself was nothing. What it revealed was everything. On September 18, 1980, at approximately 6:30 p.m., Airman David Powell reached for a pressure cap with a socket wrench. The socket slipped, and in the 3 seconds it took to fall 80 feet, strike a thrust mount, and puncture a tank wall thinner than a dime, an $8 hand tool defeated the most advanced nuclear weapon system in the American arsenal. The warhead did not detonate. The safety systems held. The lesson was learned. However, the question that Damascus poses remains unanswered. In a world of nuclear weapons maintained by human beings using human tools, following procedures written by humans who cannot anticipate every failure, how many times can we rely on luck before luck runs out?